If you look closely at the concept images and top-secret prototypes of the next generation of military aircraft, you'll notice a striking visual detail that completely changes the silhouette of fighter jets. The traditional tail, composed of the vertical and horizontal fins that have accompanied aircraft since the dawn of aviation, is disappearing entirely. This radical transformation of aerospace design isn't driven by a passing aesthetic trend, but by a desperate physical and strategic need to achieve absolute invisibility in the air. For over a century, tail fins were considered a sacred and irreplaceable element for ensuring the stability and control of any flying machine. However, in the context of modern high-intensity combat, designers from world powers have concluded that the aircraft's tail has become its most dangerous Achilles heel. The physics of enemy radar has advanced to such an extent that the mere presence of these vertical surfaces jeopardizes the aircraft's survival before it can even complete its mission. If you're passionate about the secrets of aerospace engineering, physics applied to military defense, and the invisible technologies that will dominate the skies of tomorrow, subscribe to the channel now and turn on notifications so you don't miss any updates. To understand the fundamental reason for this drastic reduction, it is necessary to analyze how electromagnetic waves work in aerial detection. The most advanced fifth-generation fighters currently flying attempted to overcome stealth by slightly tilting their vertical stabilizers. This geometry was designed to deflect signals from interceptor radars and missile warheads, which operate in high-frequency bands with very short wavelengths that easily bounce off the aircraft's sharp edges. The real problem arose with the modernization of long-range surveillance and strategic search radars deployed on the ground by rival countries. These early warning and defensive systems use extremely long, low-frequency waves designed to detect objects thousands of kilometers away. When one of these large waves strikes the vertical tail section or the right-angle junction where the fin connects to the fuselage, the entire aircraft structure acts as a receiving antenna, sending a massive reflected echo back to enemy control displays. By completely eliminating the tail fins, engineers create a smooth, integrated surface, popularly known in aviation as the pure flying wing concept. With no vertical or right-angled corners where signals can bounce, the aircraft achieves what defense scientists call broadband invisibility. This sleek aerodynamic shape allows the aircraft to evade not only short-range missile guidance sensors, but also massive long-range tracking radars, enabling it to cross the world's most heavily guarded borders in complete electromagnetic silence. Besides eliminating the dangerous radar echo that betrays the aircraft's position, removing the tail provides a huge physical benefit in terms of kinetic efficiency and aerodynamic performance. In traditional aviation, every square meter of surface area that protrudes from the main fuselage generates what engineers call parasitic drag. Traditional vertical and horizontal stabilizers create constant turbulence that slows the aircraft's forward motion, forcing the engines to burn a colossal amount of fuel simply to maintain airspeed. By completely eliminating the tail fins, the aircraft's surface area exposed to direct atmospheric friction is drastically reduced. This streamlined design allows the fuselage to flow through the air with unprecedented smoothness. As a direct result of this efficiency, the engines can propel the aircraft over much greater distances while consuming only a fraction of the fuel required by a traditional fighter jet, resolving one of the major strategic challenges in long-range theaters of operation. This advantage in air resistance unlocks another critical capability for cutting-edge aviation: the ability to sustain supercruise speeds for extended periods. Continuously flying at supersonic speeds used to require afterburners, a mechanism that injects fuel directly into the engine's exhaust pipe. This process not only depletes fuel tanks in a matter of minutes, but also generates a giant flare of fire and heat at the rear of the aircraft, making it highly visible to any search and rescue sensors. By flying without the constant braking effect of tail stabilizers, the aircraft can reach and maintain supersonic speeds powered solely by the dry thrust of its turbines, preserving its fuel reserves and maintaining a remarkably low heat signature. This minimization of the thermal and infrared signature constitutes the third major pillar justifying the elimination of the tail in next-generation aviation designs. In traditional fighter jets, tail fins block and box in the flow of fresh air directly behind the engine exhaust, trapping the heat from the expelled gas. On a sleek, tailless platform, the rear area is completely clear, allowing designers to install flat dispersion exhaust nozzles. The cool air flowing freely over the large surfaces of the flying wing mixes almost instantaneously with the burning engine exhaust, diluting the plume of heat before enemy infrared-guided missiles or heat-seeking sensors can lock onto the target. After understanding the overwhelming advantages of a tailless design in terms of stealth, range, and heat reduction, the fundamental question arises that defies all the laws of traditional aerodynamics. How on earth does an aircraft that lacks vertical surfaces to control its direction fly? Since the dawn of aviation, it has been taught that an aircraft without a tail rudder is physically unstable on the yaw axis, meaning it would tend to skid uncontrollably sideways until it disintegrated in midair. If a human pilot attempted to fly such an aircraft manually, they would be unable to maintain balance for more than 2 seconds before losing complete control. The reason this engineering marvel is feasible today is solely due to the mature development of ultra-fast computer flight control systems, popularly known as massive fly-by-wire technology. In these cutting-edge aircraft, there is no longer a direct mechanical connection between the pilot's control stick and the wing control surfaces. Instead, the cockpit is connected to a series of onboard computers with colossal processing power. These computers receive thousands of data points per second regarding wind speed, altitude, bank angle, and the pilot's intended trajectory. Based on this constant information, flight computers make automatic micro-adjustments to the ailerons, flaps, and wing leading edges hundreds of times per second. These digital corrections are so fast and precise that the aircraft remains perfectly stable and responds smoothly to the pilot's commands, completely eliminating the need for a physical stabilizer upright at the rear. However, to perform tight turns and aggressive combat maneuvers, the computer control requires additional tools to replace the turning function previously performed by the tail rudder. The first key solution is the integration of advanced thrust vectoring into next-generation engines. The exhaust nozzles of these turbines are not fixed tubes, but movable structures that can adjust the direction of the flow of burning gases upward, downward, or to the sides in milliseconds. When the pilot wants to turn the aircraft to the right, the flight computers slightly divert the engine thrust to the left, generating an instantaneous reaction force that pushes the nose of the aircraft in the desired direction, allowing for tight turns without relying on a physical rudder to cut through the air. The second innovative mechanical tool is the asymmetric air brakes installed at the tips of the large flying wings. These movable surfaces consist of small, split ailerons that can open independently on each wing. If the system needs to smoothly turn the aircraft during cruise flight, it slightly opens the brake on the right wing, creating aerodynamic drag that slows that side of the aircraft and induces a coordinated turn without disturbing the airflow over the rest of the wing surface. The disappearance of the tail in modern military aviation is not a mere design whim, but irrefutable proof that computing power and control engineering have reached a level of maturity capable of overcoming the limitations imposed by physics. Dominion over the skies in the 21st century will belong to the aircraft that achieve the perfect balance between total broadband invisibility, colossal kinetic efficiency, and superhuman agility managed by the digital mind of their flight systems. If you were amazed to discover the real reason why modern fighter jets are eliminating their tails and the engineering secrets that make it possible, subscribe to the channel immediately, like this content, and share it with your aerospace enthusiast friends to continue exploring the future of air power together. The definitive elimination of tail fins in military aviation designs marks the clear boundary between the 5th and 6th generations of fighter jets. This structural transformation demonstrates that 21st century aerospace design is no longer limited by the old rules of manual fluid dynamics, but rather responds to a complete integration of material science, electromagnetic wave physics, and computer processing power. The major global powers have understood that maintaining vertical elements at the rear of an aircraft to facilitate traditional piloting is an unacceptable luxury that destroys strategic stealth against modern radar. By eliminating tail fins, new fighter jets and strategic bombers gain a tactical advantage that extends far beyond simple radar evasion. The massive reduction in aerodynamic drag and lower fuel consumption open the door to deep penetration missions into heavily defended territories without the constant need for aerial refueling tankers. This extended range is vital for operating over vast oceanic and continental areas where Allied air bases are located thousands of kilometers from the primary target. Furthermore, the absence of vertical fins drastically simplifies the aircraft's physical maintenance in hangars. In previous generations of stealth fighters, the angular joints between the tail and fuselage required hundreds of hours of meticulous work by technicians to apply and repair the delicate radar-absorbing coatings. By constructing a smooth, continuous, integrated flying wing surface, engineers eliminate the points of greatest thermal and mechanical wear, significantly reducing maintenance costs per flight hour and accelerating the turnaround time for returning the aircraft to the air. This clean fuselage architecture is rapidly becoming the mandatory standard not only for the large manned combat platforms of the future, but also for the new fleet of unmanned robotic aircraft that will act as forward escorts. Escort drones designed under this same tailless concept will be able to fly at the front of formations in complete electromagnetic silence, acting as advanced sensors and defensive shields capable of penetrating the most dangerous missile rings without revealing the presence of the main force. Victory in tomorrow's aerial battles will no longer be decided by the stellar beauty of an acrobatic maneuver in a visual duel, but by the ability to vanish completely from the electromagnetic spectrum and strike the adversary before they can detect the first signal on their screens. The elimination of the tail represents the ultimate triumph of pure physics and computer code over the aeronautical tradition of the last century, ensuring that combat aviation continues to evolve toward ever purer, more efficient, and invisible forms. If you were amazed to discover the real reason why modern fighter jets are eliminating their tails and the technological revolution this represents for the future of air combat, subscribe to the channel immediately, like this content, and share it with your aerospace enthusiast friends to continue exploring the frontiers of modern defense together.